Okay, so administrative stuff first. So we have homework 1 due Friday, right? Lab 1 due next Friday, right? So I have office hours on Thursday after class. I can kind of hang out briefly after class today if you have some quick questions. I have a meeting at like 3, I think, back in my office, but I can hang around for a bit if you have questions about either of those things. I got some questions about like reference material for this kind of stuff, like random vectors and the probability background we're doing. So for this part, I'm generally following a book that I used when I taught ECE4670. It's this one. It's Alberto Leon Garcia. So if you're looking for a book to read, you know, his background for this stuff, this would be the book that I'd recommend. As we get into like the Digicom proper stuff, you know, I have lecture notes I'm going to post. I can try to type up my like early 4110 notes from that class and post those. Like, I don't want to promise anything though, because that's a very time-consuming thing, and probably by the time I get it done with, you know, we'll be well past this stuff. So anyway, this is the book you can use for that. Is anyone taking 4110 right now? Is this the book you're using? Okay, so there's agreement there. Okay, let's see. The enrollment is kind of creeping up and up and up, bit by bit. We're now like at 31 or something. So that's good news, to me anyway. The only potential issue is like we don't have a lot of extra seats left in this room. I mean, we got, you know, 10 of these pairs of desks, each one seats 4, and then we lose 2 here, 1 for the camera, and so we're like, I don't know, like 36 or 37 is the room capacity, and we're 31 right now. So I went over to 203, and there's like no one in there. There seems to be no class in 203 Phillips during this slot. So I might, you know, just see if we can move over there. We could spread out more. We have a huge board in that room. It would be very exciting. So anyway, I'll look into that. Friday discussion, Umair plans to do just a basic probability review. So we'll just put up some basic probability exercises and give you a chance to solve them, and then, you know, provide guidance as needed. If you feel pretty confident on your probability review, then that's not necessary. In general, the discussions are optional for this class. And then lastly, just one comment I was supposed to make in the first lecture, and I forgot. I was supposed to make it the last lecture, and I forgot again. But one corollary of the video noting is that, like, if you ask a question, you know, to some extent the microphone will pick up your question. So your voice ends up being then recorded, and other people can then hear your voice on video note. And there's some push actually for the department for us to put all these things on video on like YouTube so that the whole world can watch our lectures, in which case like the whole world might hear your question. So hopefully that's not really an issue for you. I mean, the camera's mostly focused on me and what's happening up here. But if that like kind of makes you seriously uncomfortable, then let me know, and we can discuss, you know, how to manage that. Okay, that's all I have. Any questions? No? All right. So today I'd like to, we're in the probability review right now. So, you know, general comment, we have like, I mean, you can look at the lecture schedule. We have several weeks of like background review first. So, you know, about 7 lectures or so on, you know, 8 lectures of kind of background stuff before we get into Digicom proper. So there's a bit of a kind of dry slog here in the beginning. You got to kind of, you know, bear with me for. But I promise this is not a pure theory class. Like, this is to kind of like lay the groundwork, and we will build working systems eventually. So today's agenda is to finish talking about covariance matrices. It's something we started last Thursday. We'll finish that today, and then we'll start talking about Gaussian vectors. So here's where we left off. So we're talking about moments. And if you remember, I said moments are in general a way of like summarizing a distribution, right? So a probability distribution, like a CDF, PDF, PMF, depending on what format you want to put it in, they completely describe a random variable or a random vector, right? Anything you want to compute, like any probability you want to compute involving a random variable or a random vector, you can compute from the full-on distribution if you have it, okay? As such, the distributions contain a great deal of information, arguably too much information in many situations, okay? They can be rather abstruse. They can be kind of hard to understand, hard to really wrap your head around. They can also be hard to learn from data. You just get data and you wonder, what is the distribution of this? Well, the distribution has so many degrees of freedom in it that like trying to estimate it accurately from any reasonable amount of data can be quite hard. Okay, so moments just summarize the distribution. They give you like just single numbers that just I mean, the summarized distribution in that you can look at that one number and get a sense of where the distribution is centered, how spread out it is, and so on. And also, given that there's just like one number, like one scalar, rather than like a whole function over the real line, okay, they can be estimated much more accurately from data than the distribution itself can. Okay, so that's the service they provide. That's the function that they serve. So first moment is the mean. So we defined the mean of a random variable last time. I mentioned last time that we tend to work with random vectors in this class because we don't tend to have one random variable in isolation. We have a bunch of random variables that we're operating on. And it's helpful, like both theoretically and computationally, to put all those random variables in a vector. And they can use linear algebra to manipulate them. Okay? So we define the mean of a random vector, just be like the component-wise mean of each random variable. So that's simple. It has the usual like center of mass, center of gravity interpretation, and so on. We then went to variance. So how would you define the variance of a random vector? And we said probably the first thing that pops in your head is just repeat this. Just define variance of a random vector to be the component-wise variance of each of the constituent random variables. Okay, and I said you can do that. There's nothing like, that's not wrong. Okay, it turns out to be not very useful, however. It's much more useful to throw the covariances in instead. Okay, so the covariance between a pair of random variables x and y is defined like this. Note that if x and y are the same random variable, then you get the variance of x. Right? You have x minus its mean squared. Covariance xy is covariance yx. Okay? And it's a measure of like whether the x and y random variables tend to move kind of together or opposed, right? So if this thing's positive, we say they're positively correlated, in which case this random variable inside the expectation tends to be positive in some sense. And if it's positive, that means that this random variable is positive when this one's positive. So x is bigger than its mean when y is bigger than its mean, and x is below its mean when y is below its mean, right? So they're kind of moving together in some sense. Whereas if the covariance is negative, we say they're negatively correlated. In that case, the argument to the expectation tends to be negative, right? So x is below its mean when y is above its mean, and vice versa. So they're kind of like moving opposite to each other. And then if the covariance is 0, we say they're uncorrelated, so they're not really moving together in any coherent way. And of course, if they're independent, then they are uncorrelated. Okay, so what we do instead of defining just a vector of variances, okay, instead what we do is define a much bigger object, the covariance matrix, okay, which is just a matrix with like all the pairwise covariances among all the different constituent random variables, x0 up to xn minus 1. Okay, so recall we used like the C rather than MATLAB index numbering in this class. You start at 0, go up to n minus 1. I also should have said early on that like generally all vectors are column vectors in this class unless otherwise stated. So by default, everything's a column vector. Okay. So anyway, you can form this matrix with just like all the different covariances in it, right? So the ijth entry of this matrix is the covariance between xi, xj, okay, for all I and j. Note that you have the variances along the diagonal, right? This is variance of x0, variance of x1, the variance of xn. Okay, so that object we started with, I said wasn't quite enough. That's still there. We've just supplemented it by adding all this other stuff, all these other covariances. And since covariance of xy is covariance of yx, you know, this covariance here is the same as this one, right? This one is the same as this one. Okay, so the matrix is symmetric. Right? You take transpose, you get the same thing, right? Because of this commutativity, if you want, of the covariance matrix. Okay, everyone with me? Okay, so I'm going to try to convince you that like this is a much more useful object to have hanging around than just the vector of variances of the individual variables. I'm sorry about the board. I don't know, like someone must have been pressing really, really hard with the chalk because like this stuff doesn't come out. Anyway, okay, so one bit from last time. So last time we looked at the variance of the sum of two components, and we noted that this can be written as the variance of one plus the variance of the other plus twice the covariance of the two. Like that, right? So we just did that expansion last time. Okay, and I noted this bodes well for our covariance matrix definition because if you look at the case where n equals 2, then the covariance matrix is just the variance of one variable variance of the other variable on the diagonal, and then their common covariance on the off diagonal. Right? So this formula here is essentially saying that the variance of the sum is the sum of all the components of the covariance matrix, right? It's variance plus twice the covariance. So I add all this up, I get variance plus twice the covariance, right? Okay, so I pointed out last time that that's actually a special case of a more general phenomenon. So here's our first theorem in the class. So theorem is something we prove as part of the class instead of just taking it for granted. So the theorem is if A is a deterministic vector, deterministic column vector, okay, and X is a random vector, then if I look at the variance of A transpose X, okay, this is a random variable, right? A transpose X, that's a scalar random quantity, right? It's derived from X, but it's a scalar, so I can talk about its variance. Okay, so this is A transpose Kx A. Okay, so in particular, if A is just like 1, 1, all right, then it's the same variance of the sum, okay, is, 1, 1, Kx, 1, 1, which when you expand all that together, you get just the sum of all the entries in Kx. Okay, so I think when we left off on Thursday, we were right here. So let me prove this. All right, so variance of A transpose X. So just plug in the definition of variance, right? So this is the random variable minus its mean squared, right? Okay, that's just the definition of variance. Okay. The square I'm going to write out twice. Okay, so rather than writing 2 here, I'm going to write the thing and then the thing again. So A transpose X minus expectation of A transpose X. And then just write it again. A transpose X minus expectation of A transpose X. Can you all read this with all this stuff on the board? Yeah, okay. Yeah.
From last time's lecture notes, you put like an underline under the K. What was that again?
Okay, I should have been doing that here. So I think like 80% of the struggle in understanding this material is keeping straight like what kind of object you have and like what dimension is it? Is it a vector? Is it a scalar? Is it random? Is it deterministic? Like if you just kind of keep all that straight, you're actually much of the way there. So I tried to use notation to help that. So we put an arrow above things to indicate that they're vectors. And my intent is to put underlines under matrices to make it clear that they're matrices. And I guess I started this lecture and forgot I was doing that. So thank you for catching that. Don't hesitate to stop me if it looks like my notation is not consistent. So that when I wrote the big K, it's erased now. When I wrote the big K up here, that's supposed to be K underline. Underline in general just means like reminder this is a matrix. Or it could be a matrix, I guess. Okay, other questions? So far so good? Okay, so this is the same thing. The square I just wrote twice. Now, expectation is linear, so these constants I can pull out, right? So let me pull that constant out. Let me pull that constant out. And then once I pulled it out here, I'm going to pull A transpose out again. So you get A transpose X minus the mean. Okay. And then I guess I'll have the same thing here. I guess I should have done that step first and then, expanded this square, but whatever. Okay. So just pull the A. A is a constant, so it comes out of the expectation, right? And then you have A transpose multiplying both of these, so pull it out. Okay. A transpose B is B transpose A, right? This is all real stuff. Okay, so I'm just going to swap these. A transpose X minus its mean. And then I'm going to have X minus its mean transpose times A, right? A transpose B is B transpose A. When, yeah, that's just in general true, right? B transpose with scale with vectors, I guess. Okay, so now I can pull these out of the expectation again. There's like multiple expectations here, right? They're kind of nested. So constants get pulled out of expectation. So pull all those out. Okay, and you're left with A transpose. I'm going to have expectation of X minus its mean transpose. So let me continue that up here. We have this, right? Okay, so maybe ideally I would have pointed this out outside of the proof, but there's a fact we're going to use here that this is just kx. Okay, so the way to think about that is, so think about the ijth entry of this, right? So here's the orange part, so y. So these are the ijth entry of that matrix, right? That's the covariance of xi, xj, right? Okay, well, here we have expectation of a matrix, okay, which we define as just expectation, you know, the matrix consisting of the expectation of each component, okay? The ijth entry of this matrix is going to be xi minus its mean times xj minus its mean, right? You got to kind of visualize this, right? This is a column vector times a row vector, right? So it's kind of blowing up, it's expanding out. Okay, and the ijth entry is going to be the ith entry from here, which is specifying the row, and then the jth entry from here, which is specifying the column. Okay, so like this is the best proof I can offer of this. You have to just kind of stare at it and visualize how the linear algebra is working here. So this this matrix here is just kx. Okay, so overall you have A transpose k x A. That's it. Okay. Okay, so hopefully that persuades you that the covariance matrix is a useful object to have around, right? I mean, any variance of this form you can compute if you have the full covariance matrix of X. Whereas if all you had was the variance of the components, and like all you have are the diagonal entries of kx, and then that's not going to be enough to compute a quantity like this. Okay. If you're not persuaded of that, let me show you a generalization of this. It's also quite useful. So let's suppose A is a deterministic matrix. And let's suppose y is equal to ax. Okay, so I have my random vector x. I multiply it by a. I get a new random vector. I call it y. Okay? Y will have a covariance matrix, right? Every random vector has a covariance matrix. So y has one. X has one. Okay, how are they related? How do I get the covariance matrix of y from x? It turns out ky you can write as a kx a transpose. Okay, so all you need to know is the covariance matrix of x. That's all the information you need about x. That plus the matrix that you're using to transform, those two together are enough to give you the covariance matrix for y. So in general, I mean, I can give you like a meta theorem. This isn't like a precise theorem I can write down and prove. Okay, but manipulating covariance matrices is like a closed system. Okay, and that like usually you don't need something beyond the covariance matrices in order to compute other covariance matrices and so on. It's kind of a closed little system. So here's a good example of that. Like you don't need other information about the distribution of X. Is it Gaussian or whatnot? What's it, all you need is the covariance matrix to get covariance matrix of X in order to get the covariance matrix of Y. You don't need other facts about X. Okay, so we'll do this proof too. This is almost like a repeat of the previous proof. So it's didn't quite get it the first time. So here's a second go at it. So ky, by definition, this is expectation of y minus its mean, y minus its mean transpose. Right? Definition of covariance matrix. All right, y is defined in terms of x, and I want to relate ky to kx, so it makes sense to plug in for y, right? So replace all the y's with ax. Okay, so just like string replace ax for y. All right, so now I'm going to do kind of the same, play the same game here. So this a is deterministic. Think of it as a constant. You can pull it out. Likewise for that one. Okay, then I'm going to factor a outside of that parentheses. So we'll get expectation a times x minus its mean. Yeah. That's that whole first factor becomes this, right? So I pull a out of the expectation and then factor out of the whole thing. Do the same thing here. Like that. That one has a transpose on it. Otherwise, it's the same. All right. Tell me about A, B transpose. Tell me about this.
A transpose, B transpose.
A transpose, B transpose? That doesn't dimension check, actually. Yeah, it flips when you transpose, right? Yeah. I mean, the number of rows in this matrix has to be the number of columns in this matrix, and vice versa. So it can't be A transpose, B transpose. Okay, anyhow, here's A, B transpose. So you get x minus its mean transpose A transpose, right? That's it, right? We're basically done. So the A you can pull out, A transpose you can pull out. Okay, you get A covariance matrix of X. I have X minus its mean transpose, A transpose. Yeah? Okay. This course does not involve a great deal of memorization. This is one formula it might be worth trying to commit to memory. Is it A, Kx, A transpose, Kx? It's good to commit that to memory because we'll use it a fair amount, and it's helpful to be able to just write it down without having to flip and remember. Okay, so this is one fact that I would commit to memory right here. It's one fact I have memorized. Okay, I can put it that way. Okay. So hopefully you're convinced of the utility of covariance matrices. We'll use them a lot in this class. So if you're not convinced yet, I guess the proof is in the pudding. When we go to design communication systems, we'll see it coming up a lot there. I'd like to say a few, since we're going to use it a lot, or use them a lot, I'd like to say a few other words about their property and structures and so on. So first, a quick aside about singular covariance matrices. Okay, so what's going to happen, the covariance matrix is singular. So let's suppose we have a covariance matrix of some random vector x, and let's suppose it's singular. Okay, meaning its determinant is 0 or equivalently it has a vector, non-zero vector in its null space. So I've defined this last time, right? There exists. You okay with that? It's just like shorthand. There exists. So there exists some vector a not equal to 0 such that k x a is equal to 0. Okay, this can happen. It turns out this is sort of a degenerate case that we're not really going to worry about. Let me show you why. So suppose it's singular, in which case I know there exists a non-zero a, so that this is true. Okay, consider this quantity. Consider is there a question? No? Consider this quantity, variance of A transpose X. Okay, what is this in terms of the covariance matrix of X? Just blurt it out. You can flip if you want. I mean, I don't mind. Just let me know they're on the same page here, so to speak. A transpose K, yes. A transpose. Good, thank you. Like that? All right, that was first theorem of the class, right? That's that right there. Call it theorem 1 from now on. All right, KXA, 0, right? That's 0. Variance of this random variable is 0. Therefore, the chance that this random variable equals its mean is 1, right? We noted that last time. Random variable with 0 variance is equal to its mean with probability 1. Okay. Since this vector is non-zero, it must have at least one non-zero component. Okay, let's call J its non-zero component. Okay, then if you expand this inner product as a sum, you have sum I equals 0 up to n minus 1, A, I, X, I equal to mean of that inner product. Right? And now one of those AIs must be non-zero if the vector is non-zero. So let J be the one that's non-zero. Keep that one there, move all the rest of the ones over. And you have A, J, X, J equal to this mean. Minus all the other terms in that sum. So sum I equals 0 up to n minus 1, I not equal to J, A, I, X, I. That probability is 1. Okay, all I did was take, save one term here, the jth term, move all the rest of them to this side. Okay, AJ is like by definition non-zero, so if I want, I can like divide this whole thing through by AJ. Right? Okay, so what do we have? This xj variable I can write as a linear function of all the other ones, right? With probability 1, this xj variable, the jth variable in the vector, is equal to this function of all the other variables in the vector. So I have, in a sense, a redundant variable. Right? I have one variable that is just a linear function of all the other ones. If the covariance matrix is singular, then there exists a redundant variable in the vector. Okay? In practice, that rarely happens. Okay, out in the real world, okay, and when you're doing mathematics, okay, all kinds of stuff can happen, all kinds of weird things can happen. When you're like analyzing communication systems, it's very rare that you would stumble on a covariance matrix that had this property. Nonetheless, even if it happens, okay, there's an easy fix. You just find a variable find a redundant variable, just drop it from the vector. Okay, just remove that entry from the vector, work with a lower dimensional vector. That one will usually be non-singular. If that one is singular, that means you have yet another redundant variable. So find it, purge it. Okay, keep going. Eventually, okay, if you have any randomness at all on your hands, eventually you'll have a covariance matrix that's non-singular. Okay, and the thing is, you've lost no information by dropping those variables because you can always get them back. Right? If I ever want xj back, okay, I've got it, right? Because I'm saving all these other ones, right? So there's really no harm in dropping those. Okay, so bottom line is if the covariance matrix is singular, you've got redundant variables, drop them to get a non-singular one. As such, in class, we'll just generally assume the covariance matrices are non-singular. Okay, so they have full rank. Okay. So that was just kind of an aside. Okay, let me show you a couple of properties of covariance matrices that we will make use of. Okay, so I'll show you two simple properties that covariance matrices have, and it turns out from those two simple properties, like a whole boatload of stuff follows logically. Okay. Okay, so here's the theorem, properties of covariance matrices. So if Kx is a covariance matrix, the covariance matrix of some random vector, then two things must be true. One is Kx must be equal to Kx transpose. Two, A transpose Kx A must be greater than or equal to 0 for all deterministic vectors A. Yeah. Okay. I'm not going to write out the proof of this. We've done it essentially already. Okay, we know the the ij entry of the covariance matrix is the same as the ji entry, right? Because the covariance of two random variables is symmetric in the two variables, right? So we noted this already. How do I know this is true? For every, it seems like a rather strong statement, right? For every vector A, this thing's non-negative. How do I know that? For every vector A? You're getting ahead of me, but how do I know that this is true? Any covariance matrix, any vector, A transpose times the covariance matrix times A cannot be negative. Why not? It's okay to flip back to theorem 1 if you want. Sorry. It's A variance, right? This has got to be the variance of A transpose X. So if it's a variance, then by golly, it's going to equal to 0, right? Okay. So in linear algebra speak, any matrix satisfying 1 we call symmetric. Any matrix satisfying 1 and 2 together we call what? Positive what? Positive semi-definite. Yes. Okay. If you haven't heard this term before, then no worries. So we call it positive semi-definite or sometimes non-negative definite. And the abbreviation we use for this is, I'm big into abbreviations actually, because it gets tedious to be writing all this stuff out. So the abbreviation we use when you want to say it's positive semi-definite, rather than writing positive semi-definite, okay, we do kind of a curly greater than or equal to like this. Okay, the idea is it's more curly than the usual greater than or equal to, which is just for real numbers. Here it's like a curly thing. All right, why the semi? Like, why don't we just say definite? So you can also have matrices for which, let me kind of augment with color here. You can have matrices for which you have strict inequality here for all A not equal to 0. Okay, that can happen. That's a stronger condition, and that implies the white one. Okay, and if that's true, then you just say positive definite, like that. Okay, so they reserve people reserve positive definite for that special case, and then positive semi-definite is like the more generic case. Okay. Okay, great. So it satisfies these two conditions, and people in linear algebra have names for such matrices. So what is this bias? Okay, well, it turns out you can say a lot about positive semi-definite matrices. An amazing amount, actually. Because here's a fact from linear algebra. So a matrix K is positive semi-definite if and only if K can be written as U lambda U transpose. Okay, where U is what they call an orthogonal matrix. So there's a couple ways of thinking about that. So one is if you write U as just a bunch of vectors, like U, let's say 0, U0, U1, up to UN minus 1. Okay, then these U vectors form an orthonormal basis. Okay, meaning they're orthogonal to each other and they have norm 1, length 1. Or like an equivalent way of thinking about it is just that U transpose U is equal to identity. So U transpose is U inverse. Yeah, this is a capital lambda. With an underline. Okay, so if you stare at this condition here, you'll see it's equivalent to this one, right? Because just try to visualize U transpose U, right? I mean, when you do that multiplication, you're taking the inner product between the columns of U and the rows of U transpose, which are the columns of U, right? So it's like the just pairwise inner product among all the columns of U. So saying those are orthonormal is the same thing as saying this is identity. So that's U lambda lambda is diagonal with non-negative entries. Okay, so lambda, you write is lambda 0, lambda 1, lambda n minus 1 is diagonal, so all these are zeros. And that's that. Okay, this is nothing but the eigenvector eigenvalue decomposition of K. Okay, so these, here's a different color. Okay, so these U's here, these are the eigenvectors of the matrix. So the matrix has orthogonal eigenvectors. Okay, and these are the corresponding eigenvalues. Okay, so as such, you can easily compute this in MATLAB. If you have a covariance matrix K, okay, you plug it in, you type, what's the command for eigenvalues, eigenvectors in MATLAB? It's like eig, or eigs. I can never keep the two straight, eig. Okay, you just type eig K, and it hands you U, and it hands you lambda, and all this stuff. So that's the statement of the theorem. Remember, facts are things I don't prove. Theorems are things I do prove. I'm not going to go anywhere near trying to prove this. It's just a linear algebra fact. I'll just point out that, to me, this is an amazing theorem, actually, right? Because you start with, unfortunately, I had to erase it here, just get the whole theorem up. But you start with these really bland hypotheses, right? Matrix is symmetric, and then, like every quadratic form is non-negative, essentially, right? So you start with these really like bland, kind of colorless assumptions. And then from those two assumptions, you get all this amazing structure. You have U and they're orthogonal and orthonormal, and then lambda and is diagonal and they're non-negative, right? It's amazing, actually. That like so much can sprout out from so little. Incidentally, the second assumption, the one that like A transpose KXA is greater than or equal to 0, all that does is give you this right here. That the lambdas are non-negatives. Actually, the symmetric part gives you all the rest of it. Okay, so if you delete 2 and just have 1, the whole theorem is true just without the non-negative lambda. Lambda's going to be negative in that case. Okay, so it's really the symmetry of the matrix is what hands you all this stuff. Okay, and then the positive semi-definiteness in addition only gives you that the eigenvalues are non-negative. So amazing stuff. Okay, so that's linear algebra. We're communications engineers, right? Budding communication engineers. So what do we do with this? How is this useful? So let me give you one example. So I'm going to define a transform, actually. It's called the Karhunen-Loew transform, or KL transform. That's supposed to be like an accent grave, like. All right. Did anybody come across this word before, this name, Karhunen-Loew? No? Okay. I'm not expecting you to. I'm just curious. Okay. So suppose we have a random vector. With covariance matrix. Kx, which we'll write as U lambda U transpose. Okay, and it's sort of implicit here that U lambda U transpose is the U lambda U transpose from the theorem. Okay, it's not just arbitrary matrices here. Okay, then the Karhunen-Loew transform of X is defined to be, I'll write it as Y. So U transpose times X. And the inverse transform is take y, multiply it by u. I mean, in general, taking the inverse transform means multiplying by u. Taking the direct transform means multiplying by u transpose. All right, and u transpose u is identity. Okay, so these transforms do indeed invert each other. Okay, so I'll show you why this is like a useful transform to have in a moment. One thing, let me point out one thing first, though, which is that the transform is sort of weird in that like the transform operation actually depends on the data in a way. Like, you take the Fourier transform, like the Fourier transform operation does not depend on the signal that you're taking the transform of, right? It's like a fixed operator, right? This is kind of weird in that like the transform, I'm multiplying by a matrix, and the matrix I got by taking the covariance matrix of my data and then expanding it, okay? So this is not like just a simple linear transform. It would be a simple linear transform if I was just had a fixed matrix and always multiplied any x by that u. And if I had a fixed u and you just hand me different x's and I always multiply them by a fixed u, that'd be like a more conventional transform we're used to. Here, the matrix I multiply by depends on the distribution of the x that we've got, which is kind of weird. Okay, so I just want to point that out. Okay, so why might Karhunen and Loew define something like this? Okay, so the reason you consider this is that the KL transform of x has the property that its covariance matrix, ky, which is a y, let me do this properly, Okay, has the property that its covariance matrix would be diagonal. Its covariance matrix is lambda. Hence, the components of Y are uncorrelated. Okay? Okay, so this just follows from the formula that I urged you to memorize, actually. So look at ky. Okay, y is here. So my A is U transpose. So I'm going to get A kx A transpose, right? A kx A transpose. And my A is U transpose. Okay? Now plug in for kx. So U transpose, and then you have U lambda U transpose. U transpose is just U, right? Tell me about U transpose U. It's identity. So that's identity. That's identity. So we get lambda. Okay, so the point is that coherent low F transform like takes a vector and then transforms it in an invertible way. Okay, so you lose no information. It translates it into another vector for which the components are uncorrelated. Okay, you can always go back. You can always take the inverse transform to get your original vector back. Okay, great. So why would you ever want to do that? Well, I'll show you a use later in the class, but let me just give you a listing of where it's used, because it's actually used a lot of different places. So it's useful in detecting signals, oops, in the presence of noise. Okay, and the idea is like, when you're dealing with signals which are like, think of them as like discrete time signals, so just vectors, over time. Like when everything's kind of uncorrelated over the samples, then the detection problem is really simple. But in real life, it's usually not like independent over time. You have like a certain inertia on the system, okay? And so what you do is you apply the coherent low F transform. It transforms it to an uncorrelated version of the problem. When everything's uncorrelated, then it's easy, okay? And then you can kind of switch back as needed. Actually, in the detection problem, you don't need to really switch back. You just sort of translate it, into this like change of basis, if you will, where everything's uncorrelated, and then the detection problem's easy. So I'll show you an example of this later when we start doing actual digital communication. Another useful application of this is in simulation. Okay, so let's suppose suppose you want a realization of, I'm going to say some random vector with covariance matrix Kx. Like in MATLAB. Okay, so yeah.
Sorry, what does realization mean in this context? Is it just the real components? Or are you just...
No, I mean like when you have let's say a coin flip, like a fair coin flip, the distribution of the flip is 50-50. But I can actually just like flip a coin, in which case I get the outcome, which is what we call the realization. Yeah. So for random variables, it's like the random variable might have a Gaussian distribution, with zero mean and unit variance or whatever, and then we actually realize the random variable and we get a number. So the realization is that number. Okay, so suppose I have a covariance matrix in mind, and like in MATLAB, I want to produce a random number, a realization, or a random vector, okay, whose distribution had that matrix, that covariance matrix. How would I do that? Okay, this is actually a very practical problem. Okay, so if you're in Digicom and you go work for Qualcomm, okay, You got to simulate your designs, make sure they work. You might run some experiments and say, okay, our noise, has covariance matrix whatever. Okay, now I want to generate a lot of different realizations of the noise with that covariance matrix so I can kind of test my design and see how it works. Okay, in order to do that, in MATLAB, I've got to generate a realization of a random vector with the given covariance matrix. So how do I do that? Okay, well, the idea is write kx as u lambda u transpose. Okay. Generate a realization of y, the Carhoon-Love transform. And then just set x to be u, y, right? I mean, if I can generate a realization of the Carhoon-Love transform, I can just invert it and get a realization of x, right? So if I want a realization of x, I can instead generate a realization of y and then take the inverse transform to get the realization of x, right? I can certainly do that. Now the question is it easier to produce a realization of x than it was of y than it was of x itself? Otherwise, I'm just going around in circles and not helping anything, right? So then the question is how to produce a realization of x, sorry, of y. Is that any easier? Well, remember the covariance matrix for y was lambda, right? That's diagonal. How might I produce a realization of a random vector with this covariance matrix, like in MATLAB?
Just make sure they're independent.
Exactly, right? So, in MATLAB, if you just call rand n, it'll give you like a Gaussian realization that's zero mean and unit variance. If you call it again, you'll get an independent realization. Okay? So, call this thing n times. Okay, you'll get n realizations. They'll be independent, so they'll be uncorrelated. So the covariance matrix is identity. All right? If I just scale each of them by like square root of lambda, right, then I'll have like n random variables. They'll be independent. The variances will be lambda 0 through lambda 1. So its covariance matrix will be this, and then take the inverse KL transform, right? So any covariance matrix that you want, you can create a realization of it in MATLAB, okay, by just starting with independent variables, okay, and then taking the inverse transform. So the inverse transform, the KL transform is sort of like removing the dependence among the components. Okay, so it's like a transformed version of them that are independent. So you can sort of like form that first, which is easy, and then use the KL transform or the inverse transform in this case to capture the dependence that you want. All right, there are other uses. These two are both useful in digital communications. There are others that I'll just mention briefly. So it's actually lossy data compression. Okay, we're not going to cover that in here. Most likely in the spring, I'll be teaching another class on data compression, 5620. So we'll talk all about this there if you're interested. So I can give you like a really short sneak preview, however. Okay, so like, you know what I mean by lossy data compression, like MP3, H.264 video. Like you stream video over from YouTube or Netflix or whatnot, and the video's been compressed down a lot. Okay, so how to achieve compression is without sacrificing too much in terms of video quality or audio quality or whatnot is kind of a rich field unto itself. We have a whole class in it. Okay, but I'll give you the skinny on it. Okay, so here's the really short, like poor man's way of doing lossy compression. That's pretty close to what, conceptually at least, is kind of close to what the real world algorithms do. So think about music, for instance, like think of like MP3, okay? So at a very high level, the way you compress music is you take the song, you just treat it as a big vector. Okay, let's do mono. Okay, in reality it's stereo, so you have left and right. That's not really central. So suppose it's mono audio. Okay, so you just have one vector. It's got like a huge number of samples in it, okay? You chop it up into smaller vectors. Okay, each one's maybe got, I don't know, 1,000 samples in it or something, okay? For each of those small samples, you come up with some estimate of what the covariance matrix is. Okay, you do the KL transform on it. In the transform domain, you just drop precision. Okay, so you compute the KL transform a certain amount of precision. Just drop least significant bits across all the samples. Just save that to disk. That's your compressed version. Okay, so it's like a lower precision version of the KL transform of the song. Okay, and then on the decoder side, okay, you read in all of these like KL transform coefficients. You pad out all the missing bits with zeros. Take the inverse KL transform, play it. That's it. Okay? In real life, there's kind of a lot more going on than that. The human ear has certain artifacts, and they sort of take advantage of that. And if you literally do it that way, there ends up being like a click at the brakes, so they end up doing it with like an overlapping set of transforms and stuff. Okay, so there's a lot, beyond that, but at a very high level, that's the gist of it. Okay, so that also comes down to the KL transform, and then lastly, like filtering or denoising. So like you have a signal and noise has been added to it kind of outside of your control and you want to remove the noise. So like Wiener filtering, if you're familiar with the term. This is also useful there. That's going to be covered in ECE4110 if you're taking that class. The idea again is like if you're operating in a realm where like your vectors are such that everything's uncorrelated over all the samples, and the problem's a lot easier. So you solve that first, and the way you handle the general problem is to take the KL transform to reduce it to that case, and then do the filtering in that domain. Okay. So I mean, it's the usual. I mean, Fourier transforms on some level the same thing. It's like certain problems are easier in the Fourier domain than the regular domain, so the time domain, if you will. So the same thing happens here. Sometimes whenever problems are easier when everything's independent or everything's uncorrelated, then you're often better off applying the KL transform, doing your calculations in that new domain. Okay, any questions on this? Are we good? All right, this completes this part right here. The KL transform turns out to be especially useful for Gaussian random vectors, so that's a good segue to our next little unit. Okay, so Gaussian. Okay, so we're going to say a lot about this one distribution. It's going to play a big role in our class to follow. So the Gaussian distribution arises a lot in communications engineering and in electrical engineering overall. And this is due to a confluence of reasons, in my opinion. So on the one hand, the Gaussian distribution arises a lot in practice. It's a good model for many physical phenomenon. This is mainly due to the central limit theorem, which you hopefully covered in a probability class. Yes? Okay. So the idea being that you add up many independent quantities, then the sum tends to look Gaussian. It's just a math fact. And it turns out lots of things in nature have the property that they can be expressed as a sum of lots of small independent quantities. So in particular, there's something called thermal noise, okay, that we'll talk about in this class. That tends to be the dominant form of noise that you deal with in communications. Thermal noise is extremely well modeled by a Gaussian distribution because it fits the hypotheses of the central limit theorem to a T. Okay, you're not going to get a better match up between theory and practice than that. Okay, so the Gaussian distribution arises a lot in practice. At the same time, it's extremely tractable. Okay, gives you nice answers. All right, you can do it analytically. You don't have to pump all this stuff in a computer and just get these big plots. Okay, so it's kind of a winning combination. It's an accurate model for a lot of things in practice and really tractable. So that's why we zero in on Gaussian distribution in particular among all the distributions out there. So let's start with just a review of Gaussian random variables. Okay, so we'll say X, a random variable, is Gaussian. with parameters mu and sigma squared, which has to be positive. If it is a continuous random variable with the following PDF, given by this well-known Bell curve. Okay, you're probably aware that the mu parameter is actually the mean, and the variance parameter, or sorry, the sigma squared parameter is actually the variance. So equivalently, people say Gaussian with mean mu and variance sigma squared. We're going to use Gaussian distributions a lot, so we're going to have to write this phrase a lot, Gaussian with parameters mu and sigma squared. So shorthand. Okay, the shorthand we'll use is like this. It's like a script n for normal. It's also called the normal distribution. Like that. Okay, so this means all that, Gaussian with parameters mu and sigma squared. And the 0, 1 case, 0 mean unit variance, that comes up a lot especially, so we'll call that standard normal. Okay. Okay, so that's the scalar case. Now, like I said, we tend to work with random vectors in this class, not so much scalars in isolation. So here's the definition we'll use in the vector case. So we'll say random vector x is Gaussian. Or equivalently, we'll say its components are jointly Gaussian. If it is continuous, okay, with the following density. So this is the multivariate Gaussian density I'm going to write up. You might have seen it before. Okay, so 2 pi to the power n over 2. I guess we need, okay, we need the parameters in here the way I did in the scalar case. So if it's okay, I'm going to amend this definition right here. So I'm going to say it's Gaussian with parameters mu and k if, again, it is continuous with density, and here we have k to the power 1/2. Okay, and then e to the minus 1/2, and you have x minus mu transpose k inverse x minus mu, like that. And I guess we require k to be positive semi-definite, which I guess I can put right in here like this. So we're going to require k is positive semi-definite and invertible. Okay, so k is positive semi-definite and invertible. That. Okay, which you can show is equivalent to, this is not particularly important for our purposes, but you can show this is equivalent to k being positive definite like that. Okay. Okay, so I mean, there's, you know, some details here to worry about, but I mean, bottom line is like, you know, we'll say x is a Gaussian vector if it has this density. All right. This is an overloading of the word Gaussian, right? We defined Gaussian already for a scalar random variable, and I'm using the word Gaussian again. for random vectors. There's no conflict between the two, okay? And that if you choose n to be 1, okay, then this will collapse down to the formula we had. This mu vector will become the mu scalar we had. The k we have here, this positive semi-definite matrix that's invertible, positive definite matrix, will reduce to the sigma squared parameter. Okay, so there's no conflict between the two. We should be aware of. Okay, so it is an overloading of the word Gaussian. Shorthand. I don't want to write this out all the time. Okay, so this whole thing. Okay, we'll abbreviate like this. We'll say x. Okay, tilde means distributed according to. Okay, and then we'll say Gaussian with parameters mu and parameter k. Okay. So again, don't be intimidated by this shorthand. It's just like string replace. Like this just means all this. I just want to write this all the time, so we'll just abbreviate it like that. Yeah.
On the 2 pi, is that an n?
It's an n. Yeah, n is the dimension of x.
Okay.
So this is length n. Length n.
K should be underlined.
K should be underlined. Good. That's twice today. Okay. Later we will show that mu is actually the mean. K is the covariance matrix, but we don't know that yet, so let's play dumb and we'll just call it parameters. Okay, so it has 2 parameters, mu and k. All right. Okay, so this is a rather involved formula. I'd like to do some examples to help us wrap our heads around it. So first example is, let's suppose x is length n and has components that are independent and have the same distribution, so identically distributed. Okay, the abbreviation for that's entirely standard, IID. Standard normal. Okay, so I have a vector. It has n components. The n components are random variables. Those random variables are independent. Each one is a standard normal. Okay, here's the question. Is x then a Gaussian vector? Okay, so you can answer this on 2 levels, right? On some level, like, it better be. Okay, if it's not, then we need to rethink our terminology here, right? But on a more pedantic level, it's like we've defined Gaussian. A Gaussian vector is one satisfying all this stuff. So, and then you write down this special case. It may or may not satisfy the definition. So let's see. Okay, so the test is, can you put the joint density of the random variables, i.e. the density of the random vector, in this form? So what is the density of this random variable x, or random vector x, going to look like? Okay, well, again, the density of x is just the joint density of the constituent random variables. Those random variables are independent, so the joint density is the product of the marginal densities. I know the marginal densities, right? So just multiply all that out. Like that. Actually, maybe I should do this in a couple of steps, just so we're not losing anyone. So they're independent, so the joint density is the product of the marginal densities, right? Independent random variables. Okay, now each one's a standard normal, so this f sub x, okay, is just the square root of 2 pi business. Like that, right? Okay, square root of 2 pi, I've got n of those, right? So I'm going to get 2 pi to the power n over 2 in front. That looks promising. Inside the exponents, so the product, move inside the exponent, gives me a sum. So you're going to get minus 1/2 sum over I x I squared, right? Which is 1 over 2 pi to the power n over 2. E to the minus 1/2. And then this is going to be x transpose times itself, right? Sum of the squares of the components, just x transpose itself. Is it a Gaussian vector? Yeah? What is mu and what is k? Mu is 0. What is k? It's identity matrix, right? There's like a hidden identity matrix inverse right here. And then here I've got like the determinant of the identity matrix, right? Okay, so the x vector is a Gaussian vector. And its mean is the, sorry, we don't know what's the mean yet. The first parameter of distribution is this 0 vector. And the second parameter is the identity matrix. So yes, it is Gaussian. So far, so good. Let me do second example. This one's just slightly more embellished. Suppose x has independent components that are not identically distributed. So they're independent, and the ith component is Gaussian with mean mu I and variance sigma squared I, like that. Okay, so I take a bunch of independent Gaussian random variables with various means and variances. I put them in a vector. Is that vector Gaussian? Okay, again, on some level, like it should be. I mean, if it's not, then we've kind of defined things arguably improperly. But on a mathematical level, this is a non-trivial question, right? We've defined Gaussian. It's a defined term. This distribution may or may not satisfy the constraints of the definition, so let's see. Well, since the components are independent, that first step is still the same. I still have the joint CDF equaling the product of the marginals. So that step is the same. Okay, now when I plug in, what's going to happen is I'm not going to have the same distribution for each x, right? They have different means and variances. So now I've got product over I square root of 2 pi sigma squared e to the minus 1/2 xi minus mu I squared over sigma squared I. Okay, so I just plugged in now for the Gaussian distribution with mean mu I variance sigma squared I. All right, continuing, I still have square root of 2 pi to the power n. So that part works out. I'm going to have the product of all these sigmas, right? So I'm going to have like product I equals 0 up to n minus 1 of sigma I squared. Let me write it this way. Sigma I squared, that whole thing in the square root. Okay, and then if I pull the product inside the exponent, minus 1/2. It's going to be a sum. xi minus mu I squared over sigma squared I. Like that. Okay, so that's just rearranging. What do you think? Gaussian? So one's harder to see. Possibly if I go like, sorry, that's a vector. Make it any easier? Well, suppose we cheat a bit. I know I'm cheating a bit by going one minute over here. Suppose I cheat a bit. Suppose that we think we know that that the mu parameter in the distribution is the mean, and this is and k is the covariance matrix. So what do we expect the mean to be here? The mean of the vector x would be what? Okay, let's.
With all the
Yeah, and k would be what?
matrix with the variances.
On the diagonal and 0 elsewhere, and that's exactly what happens here. Okay, I'm not going to try to squeeze this in the last minute. So we'll pick this up right here on Thursday, and then talk about various properties that Gaussian random vectors have that are useful for us. All right, see you Thursday.